All right, so today we're going to shine a light, and I mean that quite literally, on the invisible hardware that basically holds our modern internet together.
The unsung heroes.
Exactly. We're talking about the optical amplifier. If you've ever wondered how data can just leap across oceans or, feed these massive fiber networks without losing any speed, this is how.
This is the core technology that makes it possible.
So our mission for this deep dive is to get into the weeds on one specific piece of gear, the Thor Broadcast F-EDFA-24. We're going to unpack how devices like this one make high-speed, long-distance data transmission a reality for you.
Right.
So let's start there. What exactly is an EDFA, and why was this technology such a revolution?
Okay, so the Thor F-EDFA-24 is what we call a general-purpose optical amplifier. But the crucial part is where it works. It operates in the WDM spectrum bands.
DWDM, that's dense wavelength division multiplexing.
Correct. Think of it like taking a single fiber optic cable and stacking, say, 8, 16, or even way more separate streams of data on it.
Each on its own color of light.
Exactly. And this unit works right in the industry sweet spot, that 1540 to 1565 nanometer band.
So what did we do before this?
Well, that's where it gets interesting. EDFA stands for Erbium-Doped Fiber Amplifier. Before this, every time the light signal got weak, maybe every 50 miles or so, you had to convert the light back to an electrical signal, clean it up, process it, and then turn it back into light.
That sounds slow and expensive.
It was. That's called OEO conversion, and it added significant cost and, more importantly, delay or latency.
Okay, so there's the aha moment. The absence of that conversion is the key.
That's the aha moment. We're talking virtually zero latency. This system boosts the light wave itself without ever touching the data. It doesn't do any electrical processing.
And for something like a transatlantic cable, that's everything.
It's absolutely critical for those huge distances or even for feeding a complex distribution network with a splitter. That zero latency boost is what gives you that blistering pace we all expect now.
So that protocol independence it's just incredibly powerful because it's hands-off with the data. It's lightning fast. What else does that allow it to do?
Well, it makes the amplifier, as you said, completely protocol independent. It works with any optical signal in that 1550 band.
Any signal?
Any signal. It doesn't matter what the data rate is, what kind of information it's carrying. It just doesn't care. High-speed digital, high-speed analog, optical, RF, what people call it, RF over fiber. It handles it all.
Okay, RF over fiber. For those of us just thinking about pure internet data, why would an amplifier need to handle both digital data and this analog RF signal?
It's a great question. In big, complex networks, think telecommunications or cable TV distribution, the infrastructure often has to carry both signals over the same fiber.
I see.
Since the EDFA just amplifies the light, it supports both seamlessly. That makes it incredibly versatile for network architects. They don't have to build out two separate systems. Now, to push that signal across these huge networks, you need some serious power behind it. We're talking a strong 24 dBm optical power output.
And for the listener, what does 24 dBm mean in real terms?
It's a major power boost. It's enough to push that signal hundreds of miles further down the line before it needs another boost.
Okay, but if this thing is just boosting light, isn't there a risk it's just, boosting the noise and interference right along with it? How do you keep the signal clean?
That's the million-dollar question in optics. And that's where the specs come in. This unit has a noise figure of 6.3 dBd. In this field, a low number is what you want.
And 6.3 is low enough?
It's excellent. It means we're adding very, very little new distortion when we boost the light. And that's because it uses high-quality components like OFS Erbium-Doped Fiber, which is known for its quality.
So once this thing is installed, maybe miles under the sea or locked in a data center, how on earth do you manage it for the long haul?
Reliability is everything. It's designed from the ground up for that, with really good heat dissipation for a long life. For management, it's got remote control.
Through a network port.
Yep, a basic SNMP system through an RJ45 port. So a technician can be thousands of miles away, check its status, and troubleshoot it.
And I saw there's a pretty smart protection feature built in, too.
There is. If the input signal suddenly drops, like if there's a fiber cut somewhere, the unit automatically powers down the pump laser.
Which is the expensive high-power part.
The most expensive part. You only want that running when it absolutely has to. It protects the component and saves energy. So when you put it all together, what does this all mean? The Thor F-EDFA-24 is built for stability, for performance. It's what ensures that our fiber optic networks, from those massive long-haul routes to local distributions, maintain that crystal clear signal integrity and speed.
It's really the zero-latency backbone of the modern economy. So here's a final thought. Given that this one type of amplifier can provide consistent power for up to 8 or more DWDM channels, just consider this. How much of our world streaming, instant financial trading, global video calls relies entirely on this kind of specialized invisible hardware just boosting light across continents without ever slowing the data down?